So welcome to our session. This is the first day of our 2021 College and Career Pathways Conference. My name is Anita Gonzalez, and I am the Deputy Director for the New Mexico MESA program and also the coordinator for the conference. The session that you guys are in today is a session where we are meeting with Mr. Francisco Apodaca, and he is the Director of STEM at Luna Community College. So today, is the first of many. So we hope you just enjoy the presentation and enjoy the demonstration. There are a couple of housekeeping announcements to make. One, I've already mentioned about the camera. You are welcome to keep it on or off. That is your choice. But either way, we just ask that you be participatory as best as able. So meaning you can use the chat function. And if you need, you can also unmute yourself if you do have a question or whatnot as it comes up. If you're not familiar with Zoom, where you find chat is at the bottom of your screen. There should be like a little text bubble, and it works just like a text message. So we will be monitoring the chat for questions, and I'll be helping our presenter monitor that throughout the day, okay? Also, as a note, to get credit for attendance today, this is really important, is at the end of the session, so about 5 minutes till the close, in the chat, I'm going to put up a link to a separate survey, and that survey marks all of our attendance. So it's really, really important that you open that up and you complete it and you hit submit. I know I say that, but that's a really important step that sometimes gets missed so we don't get it counted. And what that does, it helps to track our attendance for the session, but it also gets you your entrance into the raffle for this conference. Okay, so with that, if you have any other questions, again, please pop them in your chat. I hope you enjoy our session today. So I'm going to pass it on over to Mr. Apodaca.
Well, thank you. Good afternoon. Hope everybody's having a great day. We are going to, let me start out by saying I originally thought about presenting you with some 3D stuff. We have a brand new 3D facility, or we're building one here at Luna Community College. And so it's kind of new, and I thought that'd be kind of cool to show you 3D, but most of you, I'm sure, have already experienced 3D printing in one form or another. And if you haven't, well, you'll get to it. So I kind of had a different thought that I'd pose to you, and I've had a lot of luck with students talking to them about geohydrology or a geohydrologic principle. It's called Darcy's Law. And Darcy's Law is the way that we figure flow underground. Water, particularly water flow, but it can apply to oil, it can apply to gas, it can apply to anything that's below your feet. And so I want to show you a cool little model that we have here. And I'll flip the screen around, the camera around in a few seconds, and I'll stand up. And we'll talk about Darcy's Law and what it means. And I particularly wanted to talk about Darcy's Law and its importance now, because as most of you know, here in New Mexico, we're undergoing a drought. We're in a severe drought here in Las Vegas. By this time of the year, I'll usually had 2 or 3 snows at a minimum, maybe more. Last year, it started snowing in September and didn't finish till May. Well, this year we've had no snow whatsoever, which has some really big implications for the summer, for things like runoff, stream runoff. Farmers and ranchers use this because that depends on what crops they grow, how much they can grow, if they're going to get water in their irrigation ditches. And so most of this stems from percolation from snow melt on top of the mountains. The snow melts, enters the ground, and then enters into the aquifer. Aquifers are geologic bodies, usually made up of gravels and sands and other geologic formations that hold water and that water travels through. And the way we found out about water, or we figured it out, was a Frenchman by the name of Darcy. His last name was Darcy. And he studied the flow of water through tubes of sand. And he came up with a pretty cool equation that equates flow underground to hydraulic conductivity. Hydraulic conductivity is how fast and how far will water flow underground through rock, through gravel, through clay, through sand. And there's different conductivity levels for different materials or different kinds of layers that occur in the Earth's crust. So because of Darcy, we can figure out how fast water moves. And not only that, but we can study flow rates of, as I said before, water, gas, oil, anything that's below you in a liquid form, we can study how fast it moves. And one of the ways that we use it is to study rates of pollution. So if we have a source of pollution on top of the ground, it filters, it flows down through the ground, gets in underground, and then flows, and we can track pollution rates. So with this cool model, we can do that. And I'm going to show you this. So I'm going to flip the camera around and show you this model. Anytime during the discussion, you can enter into chat, and I think Anita Gonzalez is going to tell me if there's a question that we may be able to answer. If you want to pipe in by unmuting yourself, that's probably all right. We prefer it if you do it through chat. That way I can get to it in a timely fashion. And I hope we get some questions about this, and let's get started. So I'm going to flip this camera, my computer around and show you this mod. And I will adjust it a little bit. You can see it. Okay. So what we have here is a model that hydrologists, and hydrologists are people that study groundwater. They tell you how much water is underground, how much is flowing, where it's going to, and at what rate it flows. So we've developed a model based on what's underneath your feet. So let me tell you a few features about this model. In here, this is water that feeds the flow through this model. And water will go from this side, from my right or your left, and exit here. So it goes down gradient. So it goes from the top down toward the bottom. That's a gradient. So a hill is a gradient, and water travels along much like people do on a hill, go downhill. In this model, we have different layers. Up on top, you can see coarser sand that represent rock and sand there on the surface. Then you get finer sand that's moved down through by geologic action. And then you get large clumps of sand or areas of sand. And then you have this dark layer that's right here. And this is called the aquifer boundary. So that's an impermeable layer. Impermeable means that water does not go through that layer, nor does it rise up through the layer unless we put in wells. So that's the aquifer is where most cities, Albuquerque gets a lot of water from its aquifers, Las Cruces. Las Vegas is one of the few areas that gets most of its water from a river, from the surface. Although Albuquerque gets some of the water from the surface, most of it in Albuquerque, most of it in Las Cruces comes from underground wells. Now, if you look at this model, you see these lines here. These represent wells, or in hydrology, we call them piezometers. A piezometer is a way that we can measure flow. We can sink a well down, and you can see that some of these wells go down below this aquifer boundary. And you see how water moves up and down through the wells. It's a little hard for you to see the water, but let me explain a couple other features. So you have the wells. This feature here is a lake. This is representative of a lake. This feature here is representative of a pond. This circle here is an underground storage tank. So years ago, a lot of gasoline stations stored their gasoline in tanks that were below the ground that then were fed up into the pumps that you got into your car. That's the way you got gas. Well, these are made in back in the 50s and 60s. These were made out of metal. And what happens to metal when water hits it? It rusts. So then these storage tanks began to be areas where pollutants entered into the system and then damaged the water system. They polluted the water underground. So if those places that got their water from wells, they had a good chance that their water was going to be contaminated. And if you contaminate water, and if you contaminate a well, it's done. There's very few things you can do to clean it up. So the way we study this, and we study flow, is by using a dye. So I'm going to use a little bit of dye here. I'm going to take a syringe, and I'm going to draw some dye. Well, I'm not going to do it that way. I'm going to pour some water in here and then draw it up into the syringe, some of this dye, and draw it up into the syringe. And I hope you can see this. And I want to choose red because I think we can view it. And I'm going to inject this dye into a well. So let's choose one near, we'll choose one here near this storage tank. Now you can see the dye has gone down through the well and it's starting to leach. You can see down here at the bottom of the well, it's starting to move. I'm going to take a little bit and put it in the one next to the storage tank. Or let me put it in the storage tank. Now I've got this system closed, so there's no water flowing through it. I'm going to open up the system by opening up a valve here on the lower end so that the water will move through the model and you can see how water moves. So as you see this level going down, it's called the hydraulic head. That's the difference from the elevation where the water is coming in to where it's flowing out. Now that I've opened it up, you can see how this is starting to migrate through the sand. This is the same thing that happens underground in a water system. If we have a well that's polluted, then it'll start to flow underground and it'll start to affect other wells. You can see here in the story around the storage tank, it's starting to leach a little bit, starting to come out. Let's take a different color dye and do something else. This well here, you can see this dye is not traveling down very fast because this is below the aquifer and there's water pressure that's pushing up on it. So it's protecting a little bit of the aquifer. It has to break that pressure and then go below the aquifer. It will eventually, but because of the pressure of the system of the water, it won't let it. This one above the aquifer, it's starting to leach. Now it's come to the second well and it's traveling and it's starting to get below the aquifer here a little tiny bit, if you can see it. This is pretty representative about of what happens underground. As I've opened up the system, this represents what's happening. The water level when we started was up in here on the lake, and now it's dropped because water is being pulled out of the system. It's the same thing that happens when we overuse a water supply and it starts to drain lakes. We have a lake here in Las Vegas called Story Lake that's usually very high, very deep, but we haven't had any rain here in a couple of years. And now the water level is dropped because people are drawing the water, and the water draws into the aquifer to feed the wells. See what happens if I inject in a well on the other side of the lake. You can see that that one's gone down below the aquifer. It's being pulled, whereas this one hasn't yet. It's pulled down here because the hydraulic head is lowered. You can see how it's starting to pull through the aquifer. Now we've polluted this aquifer. Anything below, if there were other wells on the other side, we couldn't use this aquifer anymore because now it has contaminants in it. This is what happens in real life situations. I'm going to take another color of dye. And I'm going to add it to a different part of the system. So now I'm going to go between the pond and the lake, and you can see that the lake is draining. And I'm going to use a different color dye so you can watch the total impact through the system. You can see this, the water pressure is forcing it back up because we've got water coming down gradient from here down. So there's pressure that's forcing that water back up in that well. But it still got to the bottom, it's still starting to pollute and starting to contaminate the area below it. Hasn't been very long since we started this first dye, and it's already traveled about a third of the way through the model. Darcy's law, we can figure flow, because Darcy's law says flow is equal to the hydraulic conductivity. That's how many feet per day water moves through the system. By the hydraulic gradient, the difference in elevation where the water comes into where it leaves, that's your gradient. We can figure that slope out, and we can figure that, the change in gradient. And then A is the cross-sectional area. How far is this from here to here? So we could figure the rate of flow using Darcy's equation. And that's what Darcy told us we could do. And this was in about 1860. So it's been around for 150 years almost. And it still is proven today to be a classic example of a model that works. So Darcy's equation is used in hydrology to study flow rates, and we could study these flow rates. If you look at this, the blue is now starting to seep, and it's being blocked by the aquifer. It won't go deeper than that, and it'll flow along that aquifer boundary to here. This is below the aquifer. Now it's starting to pollute the aquifer, and that's not good. We don't want to pollute aquifers. We want to keep pollution above an aquifer, above the permeable. This is called a non-permeable layer. Here it's represented by a clay layer that won't let the liquid pass through. unless we allow it. In this case, we allowed it by drilling holes into it that are representative of wells. The deeper wells that you see are usually representative of city-type wells to feed a lot, to give a lot of water to a lot of people. They're typically deeper, they cost a lot of money, and they're usually bigger in diameter, so you can get a lot more water out. The shallower wells are more representative of farm and home type of wells. They're typically shallower, they're less costly, they don't go into the deeper aquifers. Those are the ones that have more likelihood of pollution. What happens if we pollute more of them? See, let me choose one we haven't done yet. So now the shallower well, you can see less pressure. The buildup on it is almost more immediate, and it has a wider area of dispersal. Because this is probably less compacted. The farther you go down in the geologic record, the more pressurized the system is, so it contains most of those pollutants. If you can see, it hasn't traveled, it's a steady stream from here, but it hasn't gone far. In the aquifer, it's dispersed. Here, it's bouncing along the boundary and coming over, and this one, it's polluted the aquifer at a different level. Let me add some more recharge water here on the lower end of the head. We'll increase the flow rate and recharge this side of the model, and we'll watch it. Now you see that as we get more fluid, it's raised the hydraulic head on this well to come up. So you move the pollutants back up. Same thing with this. Let's see what happens as we follow. I can also increase the rate of discharge and increase the flow. And we'll be able to see, look what it did with that rate immediately. It almost took over quickly as we increased the flow. And this is what happens if we had more water entering the system. So we got snow in the mountains, it melted, and it's entered into the geology and the geohydrology into the system. Its flow rates increase across the model. And this is really similar to what actually happens underground. Let me try something else. Let's try some direct pollution on a surface. So I'm going to pour some dye directly on the surface. So it would be kind of like you pour a barrel of oil on the surface. So immediately it came down and it started to flow. It's starting to flow, and it's going to start to flow into the lake. That's direct pollution. Because we've been increasing the flow, I'm going to add a little bit more volume to the lake here.
Who do you have for third? Mr. Branch. How come you didn't have him sign it?
Clean out my mess a little bit. So as we've added more water to what is the lake, representative of the lake, you can see that it's actually increased the spread of the pollutants down into the vicinity of the lake because the pressure of the system draws it in. You can watch how these flows have steadily started to go down gradient. And here you can see what the gradient is by following the pollution. So that's the angle of the gradient, the hydraulic gradient. You can see here how it's discolored off the storage tank, how it's discolored or polluted all that sediment that's below it. So these are representatives of gravels and boulders, large stones underneath the, where water can flow at a faster rate, and it spread the pollution throughout this area. So you've got a plume of pollution. When you hear people talk about a pollutant plume, this is what they're talking about. What's that rate of dispersal? How far has it gone through the system? When we poured it on the ground, look at the plume that's here. That's a pretty good size area of pollution. How would you deal with it? Anybody have any idea? How could we deal with this plume here so it doesn't pollute anymore underground?
I don't know if you're able to see the chat, Cisco, but I can read them to you. It says,
yeah, read
one
them to
question
me.
is drain it out. Logan says to drain it out.
Logan, you're right, but how do you drain it? We could use existing wells because we know that this well, but this is too deep. There's a well here that's below that we may be able to catch it from. So if we put a pump at the top of this well to pump all that water, it should suck that plume over and out. So you're right.
Another student, Logan, we have two Logans with this. Logan Rowland said, with the well.
With a well, exactly. With a well and a pump, you'd have to pump it out. So I have to put up a mechanical system here on top to go ahead and pump it out because it won't flow up. Water doesn't flow up. So you'd have to actually put a mechanical pump to pump it up and out. What do we do with it after that? We have a bunch of dirty water. We can't dump it back on the ground because it's going to cause more pollution all over again. What do we do? What's the solution? What do you think?
There was those suggestions to recycle the water or to filter it.
Recycling and filtering are probably the same type of effect. So you want to take it and filter it through a series of filters. and use a process called reverse osmosis. Reverse osmosis, we put a barrier that allows molecules, water molecules, to go through and be filtered, and it keeps in the bad ones. So it would let water that's not attached to a pollutant, say in this case oil, and we'll use oil. If a water molecule is attached to oil, it's going to be bigger, so it wouldn't fit through a filter, and we could use osmosis or the flow to filter it. We could use other filters like sand filters. Many swimming pools in the 70s that were built used a lot of sand filters. So they filtered the water and went through sand, and it captured a lot because the pollutants or whatever would adhere to the sand grains, and then you clean the sand grains. It still leaves you with the pollutants. Now, if we filtered them, could we recycle the oil in this case? What do you think? Yes.
Maybe and a yes.
No, you could. There's processes that take oil and recycle it all the time, and they use filtration systems and things called deflocculants. You know have you ever heard that word before? A deflocculant? A flocculant is something that would come and stick to itself. So clay flocculates. If I put clay in water and I shook it up until it was dispersed, until the clay was in the liquid, as we let it dry, then the clay flocculates, because the clay are really fine, thin sheets of material. They stick to each other, they flocculate. So that means once they're together, it's hard to get things out. But we can deflocculate, take them apart so that we get more water out, and then we can extract the pollutants. In this case, clay was the example. We can extract that clay from the water and have cleaner water. Same thing with oil. We can deflocculate oil, we can move it away, and we just deal with that in a separate process. Or we can recycle it and take off the deflocculant. Anybody know a good example of a deflocculant? Pretty common. Dish soap. You hear the commercials all the time. They use soap to get grease off of pans or off of dishes. That's a deflocculant. So tonight when you go home and your mom's making, or your mom or your dad are making dinner, afterwards you can say, can I deflocculate the dishes? That means let's get the grease off and clean the dishes. So one of the chemicals that was developed as a deflocculant for oil was made by a chemical company, Dow Chemical, and it's a very famous detergent, and it has really interesting properties. It's called Dawn. How many of you have heard of Dawn dishwashing soap? Dawn dishwashing soap was made specifically to take and deflocculate oil. So it just turned out that when they made this solution to deflocculate oil, they thought, wow, we could add some other detergent to it and make it a dish soap. And it works really well. One of the first uses was in Ohio, near a chemical factory. They use a lot of beef fat, beef suet, or beef renderings in a lot of chemical processes, and they use it a lot in making tires. They had an accident where a truckload of this beef fat A truck got in an accident and busted the tank open, and they couldn't get it off the road. This road was slippery. People were having all kinds of accidents. So Dow Chemical had just invented this stuff. They sent a truck loaded over to this place in Ohio. They poured it on the road, and it took the oil right off the road. That's an old story, and that would happen in the 1970s. It's a true story. So let's see what our model is doing now that we've recharged a couple times. You can see that the pollutants have gone through the well, and now we have these massive plumes. Some of them have dispersed. This one's still working here on this corner. I don't know if you can see it very well with this tube. Let me see if I move that tube a little bit. You can see a little bit of it. I can see it. This one is dispersed to the top of the aquifer because you have pressure from the bottom on the water. It's going to float on the top. So that would make it easier to pump out. The blue one is dispersed, and it's dispersed through the system. The oil that we poured, or the dye that we poured on top of the ground, has now really plumed all over the place. And it's going to start to pollute these wells, and it's going to start to seep into the lake. Because we don't have any hydraulic head to pull the rest of this out, because our hydraulic head comes below the storage tank, we can't pull any more pollutants out. So we'd have to pump those out and then dig this out because we know it's bad. We have to remove this storage tank so it doesn't cause any pollution in the future. The point being, we have to watch very carefully what we're adding to systems. And the system being the groundwater system, or the ground system, and your geology right below your feet. Anything you throw on the ground is going to go straight down. It's going to end up with plumes like this somewhere. Back when I was a kid, which is a long time ago, people would drain the oil in their cars and they just throw it on the ground. We had no idea back then what we were doing. That was direct pollution, much like when we poured the dye on top of the ground here and watched it form this big plume. So we've polluted all that water. We can't use it. We can't use it for drinking. We can't use it for farming. Can't use it for livestock or cattle. It's done. So we've just eliminated one of our water sources. Not only from this model can we calculate flow. This is used in a lot of colleges. This same model is used to calculate flow. They make students go through and use the equation, apply the equation, and figure the flow rate for the model. That's we can get into really evolved and involved mathematical calculations when we're figuring flow, depending on the type of material, type of rock, because the flow rates for volcanic rock, so igneous rock, and metamorphic, so those that are around volcanoes, versus sandstones and shales and limestones are different. So we have to know what kind of rock we're dealing with that's underneath us when we're talking about flows, so we can figure out what the flow rate is, how it goes, and how far we can actually measure how far a pollutant can travel based on those flow rates if we know what's underneath us. So this is a very powerful model to use. It's kind of cool to watch. Kind of gives us some insight as to what's happening underneath our feet. And it gives students like yourselves some insight into what pollution actually does underground. One of the big things now is near Clovis, New Mexico, on the eastern side of the state, there's an Air Force base. And on that base, when they used to have, there was a jet fighter training base. when you're around jet fighters that are going fast and taking off fast, there's a lot of fires. They used to put the fires out with a type of firefighting foam. Well, the foam turns out to be a pollutant because as soon as they spray it on the ground to put out the fire, it went into the ground and it's left these huge pollution plumes, much like the one you're seeing here, wherever it is, much like the one you're seeing here, but of a chemical component in that foam that they used to fight fires. So there's a big lawsuit. These farmers were noticing their dairy cows, because they were taking water from wells to give to their cows, and they were dairy cows, so they were getting milk from these cows. People were getting sick. So finally, they made the connection between the firefighting foam that they used at the Air Force Base and they connected it with the water used for cows and made the connection because they could calculate the flows using Darcy's law to figure how far and how fast the pollutant plume is before they pump it out. And that one's going to be a complex problem because we don't know how to extract the water. So once you pump the water out that's polluted, we don't know yet how specifically to treat it to take that firefighting foam, the chemicals used in the foam, out of the water. So we're going to have to find a place to store the water until we figure out a way to treat the water. It's very complex problems. These are problems that hydrologists deal with. If you want a job that's going to give you a lot of return, that's very complex and a lot of mathematical formulas, you want to go into hydrology. And that's the study of water movement underground. It's a specific branch of geosciences. Do we have any questions?
While they're maybe typing some in, I have a question actually. Luna is the only community college that we have a premier session here with us. So maybe if you could go a little bit into just, if somebody wants to go to college and get a STEM degree, how a community college can help them with that. Like what can your role be with a STEM degree, either a 2-year and or a 4-year?
Good question. Well, here at Luna, we're in Las Vegas, which is a beautiful, beautiful community, and it's a good town to come to school in. We are a 2-year school. We are a 2-year college. And in our STEM program, in our STEM department, we have 4 different programs that you can go into and get a 2-year degree. It's mathematics, computer science, general science, or pre-engineering. Most of our computer science graduates go to work directly, and most of them go directly to work for Sandia and Los Alamos National Labs. So they get good jobs and they continue on, and then they can continue on to get their 4-year degree. In the other fields, such as mathematics, general sciences, either concentration in biology or chemistry, or pre-engineering, most of our students here go on to a 4-year college. So they either go to New Mexico Highlands University here in Las Vegas. A lot of our students go to New Mexico Tech in Socorro to study higher level STEM degrees. And some go to New Mexico State and Eastern New Mexico. Most of our computer science graduates that want to go on to a 4-year go to Eastern New Mexico. They have a very good computer science program there. The difference between a 2-year and a 4-year college, a 4-year university, is big in that it's money, cost. And here's the big game that we play here. We want you as students to save one big thing. Money. Money is the game. If you're a student in New Mexico, you can get 2 years of college or university paid for. That leaves you 2 years that you'll have to pay for by either taking out student loans, getting scholarships, working while you go to school, or you have parents that send you to school or a benefactor. Here, we like to encourage our students to start in high school. How many of you know that who knows what year you can start college classes in high school? Anybody know? Between your freshman and sophomore years. Your second semester of your freshman year, if you've got good grades, or the summer between your freshman and sophomore year, you can start taking college classes. What we like to encourage our students that are high school students is try to finish your 2-year degree while you're still in high school, because it costs you $0. If you get into what's called the dual credit program, you can take college classes for free. So that means that if you can start between your freshman and sophomore year, by the time you're a senior, you will have paid for your degree, a 2-year degree, through the dual credit program. In other words, your high school pays for your college classes. If you can get a degree by the time you're a senior, and we have a lot of students that do. I was just speaking to one who's a high school student here at one of the local high schools. This May, he'll graduate from high school, and he'll get 2 degrees from Luna in pre-engineering and math. What does that mean? That means that when you go to a 4-year school, you're already a junior at a 4-year university. You only have 2 years to go. You've used none of your financial aid, and you can use all that financial aid to pay for the rest of your 4-year degree. You can get out of here by paying $0 money. That's the game we want you to play. Pay for college, or your cost for college is $0. You pay $0 for college. That's what we want you to do. Our degrees from here are fairly competitive. We have a high bar in our math and our pre-engineering and our sciences. You come here and we teach you the rudiments to get you through and excel at a 4-year school. We want you to be the best students you can. So here at Luna, we have a different approach to classes. We have rigorous education. That means it's hard. You're going to study a lot, but you're going to learn a lot, and you're going to be prepared for New Mexico Tech or the University of New Mexico or Highlands, Eastern, or New Mexico State. You're not only going to be a good student, you're going to set the curve. You're going to be at the top of your class. That's what we want to see. And that's what we strive for here, is to give you the best education that we can. That's why we have things here that are, we're building, let me turn the camera here so you can see a little bit. Those are some of our 3D printers. So we have carbon fiber printers, PLA printers. So PLA is a material that's kind of a spongy, squishy stuff. We have plastic printers that print out plastic things. We're going to have a CNC mill, so we can do steel. So essentially what we'd like to do is a pre-engineering lab is we want you to take and go from a plastic part, create a plastic part, make it into carbon fiber, and if you need to, make it into steel, so that you can look at the manufacturing process and you understand every piece of that process. So when you leave here, you have all those tools that you can use. So we like to think of ourselves as setting the bar, a rather high bar, and we partner with very few schools, but we partner at the highest levels we can. So we also partner with Los Alamos National Laboratories. We do a lot of grant work for them. We do a lot of things here that normally is not done at other colleges. So we like to think of ourselves as having a fun time, but we challenge you to do the best that you can here. Any questions on that? If none, I'd like to invite you to come up to Las Vegas, come to Luna Community College, come and visit me. My name again is Francisco Apodaca. I'm the director of the STEM program here. We'd like to have you come and visit. Luna has degrees, other degrees also besides STEM degrees. We have a very good, highly rated nursing program. We have an allied health program that will get you into pre-nursing or to nursing. It also does EMT, and we're trying to get into paramedicine. We have a good humanities department with things like sociology, psychology, criminal justice, and we have a really good career technical area where we study things from welding to furniture making to auto body repair and auto repair. Culinary arts, but we even had a quilting program. You wanna sew quilts? That's really a form of mathematics because that's a fractal image that they use. I like to visit there all the time and see what those people are doing because they have some great images. Any questions? Any final questions?
No, well, while we're waiting for anything to come up in the chat, I did in the chat for anybody that is here, I did go ahead and put in that attendance survey link. So make sure that you go ahead and open it up, and that's going to give you your guess and feedback, but also your credit for participation today. And so I think, unless you have any last closing comments, Mr. Apodaca, I think we might be done.
Well, no, I want to thank you for listening. I hope you got something out of our little demonstration. I'm going to turn it back to our little model here so you can see how things have gone. And we go from there. But I want to thank you for your attentiveness. Thank you for participating today. Come to see us at Luna. You have a great afternoon.
There is one question about your model, though. Is there a possible way to stop the polluted water from migrating through the ground? And I guess along that, yeah. So.
Well, the obvious answer is not to pollute. Is try to stop pollution at its source. We don't want to have any sources of pollution because then we have to deal with it. Once it gets in the ground, then we have to extract it some way. It's either digging it out if it's shallow. In the case of a storage tank, we can dig it out and stop the pollution and replace all the, we have to take all the dirt and gravel and everything around it out if that's polluted. We can put in wells that would suck the water out and take out the polluted water, so we clean up the aquifer that way. It's very costly and it's not perfect. The best way to stop pollution, don't pollute. That's the easiest, quickest, and safest way. If we handled pollutants before they became a problem, we'd have a much better system to work in. But mistakes happen, people happen. We do things before we know what we're doing. You know, the Air Force didn't know that foam firefighting fire retardant was a pollutant. Took years to find it out. People didn't know about throwing stuff on the ground. You know, when I was a kid, I told you we used to throw oil on the ground. We thought, well, we can't see it, out of sight, out of mind. Well, that's not right. So the best way, don't pollute.
Thank you, thank you. So with that, that is the close of our session. Let me go ahead and stop the recording.